Good evening, students. So we'll get started with the next chapter, that is thermodynamics. So as I mentioned in the previous class, this is a very, very small chapter. Okay. Right. So it is chapter 12, which is also called as thermodynamics. If you try to break the word into two parts, thermo refers to heat, dynamics refers to flow. So if there is a branch of physics where there is a flow of heat or utilization of heat which gets converted into useful amount of mechanical work, then this branch is what is called as thermodynamics. So if you observe between physics and chemistry, you would have learned this chapter in chemistry also. So in physics, if you observe, we will be mainly concerned about how much work is generated out of the given amount of heat. Whereas in chemistry, you would have been concerned about mostly entropy and enthalpy. Right? That is why we don't concentrate here much on entropy and enthalpy, because those things are something which are related to reactions. Okay. So here we will be concentrating only on the mechanical aspects. That is the physical aspects of the particular material. Right. So there are some basic terminologies that we are supposed to understand. So the basic terminologies that we are supposed to understand is first, it is a thermodynamic system, right? So when you talk about a thermodynamic system, it is something like this. Any system, please write it down, which consists of matter arranged at certain values of pressure, volume, and temperature is what we call it as a thermodynamic system. Right? Secondly, so I think it is self-explanatory, right? When we speak about a thermodynamic system, it is a self-explanatory factor. So when we say matter, here the main matter that we be concerned about is gases. We'll come to that. Right. So any system which consists of matter arranged at certain values of pressure, volume, and temperature is what is a thermodynamic system. And these variables, that is pressure, volume, temperature, and there is something called as internal energy. So all these things, if you observe, these are some variables which are used to measure the thermodynamic state of a system. Right? So that is why these are called as thermodynamic variables. We call it as thermodynamic variables or thermodynamic state variables, or you can also call them as thermodynamic coordinates. right? Next. So we saw what is thermodynamic system. We will see what is called as a surrounding, right? So surrounding is anything outside system which can exchange energy with it. So if you talk about anything outside the system which can exchange energy with it and has a, a direct effect on the behavior of system is called a surrounding. Right. So basically, when you talk about system, they can be classified into three types. One is called as an open system. One is called as a closed system. One is called as isolated system. So what do you mean by open system? Suppose, let's say I have a cup of coffee, right, which is kept open to the surroundings. Then what is going to happen? Then there is going to be some energy as well as some matter that can get exchanged with the surrounding. Let's say if it is hot enough, then you can see some particles popping up. So when those particles are popping up, I can say that there is an exchange of matter taking place with the surrounding. So if matter plus energy exchange with surrounding takes place, then we call that as an open system. Then what is a closed system? So closed system is something where matter is not exchanged, whereas heat or energy is exchanged. Whereas energy is exchanged. Then what is an isolated system? So isolated system, as the name suggests, it has no connection with the surroundings. Right? These three are important words. Okay. So write it down. Next. What did we say? Third one, right? The fourth important point I need to talk about is boundary. Suppose I have a system and I have surroundings. In between the system and the surrounding, if there is a wall, okay, in between the system and the surroundings, there is a wall, and if heat is exchanged between system and surroundings, then the wall is said to be diathermic. Right? So if there is an exchange of heat taking place between the system and the surrounding, heat, then it is said to be diathermic. Whereas if heat exchange is restricted between system and surroundings, then the wall is said to be adiabatic.
Sir,
Tell me.
sir, what is the difference between diathermic and conductive wall?
Diathermic and conductive.
Yes, sir, conductive wall.
They have no relevance, no. What do you mean by conductive wall? Conductive wall means it will allow the matter also to flow through it. Here, in case of thermodynamics, we don't generally use the word conductive. We only call it as diathermic because we are not talking about the matter moving. It is only the energy that is getting exchanged.
Okay.
So in thermodynamics, there are only two types of walls. One is diathermic, and the second is this thing, adiabatic. Okay. So this thing, heat, does not take place, then it is called as an adiabatic. Adiabatic is an example, something like this. Like, let's say you want to take hot water, right? Let's say you're going on a trip and you want to take hot water. You take it in a material, like you call it as a flask, thermoflask, where the temperature of the water is maintained for a longer duration. I can't say it is maintained for 3-4 days and all. Maybe you can maintain it for hours together. Then that kind of a wall is called as an adiabatic wall, but it is not 100% adiabatic. That is why if you see, after some amount of time, you can say that there is exchange of heat taking place. Okay. So an example is thermoflask. Okay. Next is, so fourth one is this thing. So I'm introducing all the terms, okay? If you know these terms, concepts are very simple. It is only 2-3 derivations. So listen to this. When I talk about internal energy, so generally when you take a thermodynamic system, when I take a system, the system contains particles, and these particles possess kinetic energy, potential energy, basically these two only. Yeah. These particles are going to possess kinetic energy and potential energy. So if you are able to define the sum of potential energy and kinetic energy of all the particles in the system, then that energy is what is called as internal energy, and internal energy is represented by the symbol U. So U is equal to EP plus Kp, where EP stands for the potential energy and Kp, Kp, Ek. So EP stands for potential energy, Ek stands for kinetic energy. Done? No. We are going to see the laws of equilibrium. Right? So when you talk about the laws of equilibrium, there are basically 3 laws. One is called as the zeroth law. The zeroth law also speaks about thermal equilibrium. Okay. So zeroth law or thermal equilibrium. The next one is called as first law, which is based on conservation of energy. And the second law of thermodynamics. So basically, these are the 3 laws that are going to be discussed. Okay. So now we are going to start with the zeroth law of thermodynamics. So when I talk about the zeroth law of thermodynamics, let us consider a system like this. So before that, I need to explain what is thermal equilibrium. So can someone tell me what is thermal equilibrium?
The temperature between system and surrounding will be same.
Yes. So basically temperature remains constant. Okay. So what happens here is, if at all, this is how the law is stated. A, B, and C. If A and B are in thermal equilibrium independently, A and B are in thermal equilibrium independently, B and C are in thermal equilibrium independently, then A and C are in thermal equilibrium. Then we can conclude that A and C are in thermal equilibrium. That is the meaning of this. Okay. So this is the actual interpretation meaning of it. Right? This is the interpretation, or this is the meaning of zeroth law of thermodynamics. So based on this, the statement is given like this. The simplest form of statement is two systems in thermal equilibrium with a third system are in equilibrium with each other. That is the meaning. Think about it. So write it down. Just give me a minute. Okay. So I hope you are done with zeroth law of thermodynamics. Now, I need to tell you some more important terms of thermodynamics. Okay. First, you need to know what is called as equation of state. Okay. Let me explain what this equation of state is. So, it is a mathematical equation. So, it is basically a mathematical equation which connects the pressure, volume, and temperature. When I say temperature, I'm talking about absolute temperature, which is measured in Kelvin, of a gas. Okay. So if I'm talking about a mathematical equation which connects the pressure, volume, and temperature of a gas, then that equation is called as the equation of state. The best example is the ideal gas equation. PV is equal to N into R into T. If you see, there is a mathematical equation that relates the pressure, volume, and temperature. Right? So pressure into volume is taken to be equal to number of moles times the gas constant multiplied with absolute temperature. Right. Second is called as an indicator diagram. So it's called as an indicator diagram. So a graph drawn between any two thermodynamic variables taken at a time. Right? When you draw a graph between any two thermodynamics variables taken at a time is what is called as indicator diagram. For example, if I take a graph between pressure and temperature, if I take a graph between pressure and volume, if I take a graph between volume and temperature, all these are called as indicator diagram, and this is C, most commonly used indicator diagram. It's also called as a PV graph. We write it like this, PV graph, or this is called as P-T graph, and this is called as VT graph. Yeah, done?
Sir, can you scroll up a bit?
Yeah.
Sir, the equation of a state. Yeah, thank you, sir.
Yeah. So this second thing. Third, we need to know what is an isothermal process. So what is an isothermal process? It is a process in which temperature of the system remains constant. Okay, so isothermal process is basically a process where the temperature of the system remains constant. So for an ideal gas, we know that PV is equal to N into R into T, right? So N is the number of moles, R is the universal gas constant, and if T is the temperature, can I conclude that P into V is always a constant, right? So this law is also called as Boyle's law. I'm sure you would have known from your chemistry. So the product of pressure into volume is constant, means if the pressure increases, volume is going to decrease, and the vice versa. That's what Boyle's law states, provided the temperature of the system is maintained constant, right? So this PV is equal to constant represents Boyle's law, which is under isothermal conditions. So that is one way of understanding. Similarly, can I say that delta T is equal to 0? So delta T is 0 means what? The change in temperature of the particular system is 0. Okay. Fourth, we will take isobaric process. So what is isobaric? Iso, same bar is pressure. So any system or any process in which pressure of the system remains constant. Right. though other variables can change, is what is called as isobaric process. Isobaric process, what is going to be constant? Pressure. So the change in pressure is going to be equal to 0. Right. Fifth is isovolumic, or the commonly used word is isochoric process. So when I talk about a process, you talk about any process in which change in volume is 0. Change in volume is 0. It's called an isochoric process. Delta V is equal to 0. Okay. So we have seen isothermal, isobaric, isochoric. So what is the next type of process that is possible? Any guess? Any guess?
Sir, adiabatic.
Very good. It is adiabatic process. So what happens in adiabatic process? Any process in which delta Q is 0, that is no heat exchange takes place, is what is called as an adiabatic process. Right. Next. This is the most important one. Work done. Okay. So work done, when I talk about, is going to be something like this. So basically, when I talk about work done, I can talk about a system where there is cyclic process taking place and non-cyclic process taking place. So what is the difference? So when you talk about cyclic, initial and final state of the system are same. Okay. Whereas when you talk about a non-cyclic process, initial and final state of the system are not same. Means in a non expansion will take or compression will take place. Whereas when you talk about a cyclic process, expansion plus compression will take place. Okay. So having said this, we will start with work done by a gas during expansion in a non-cyclic process, because this, if you understand, then we can understand easily for a cyclic process as well. So when I take a container and the container is filled with gas, and the gas a container is filled with a fitted with a piston which is frictionless, right? There is pressure inside, and let's say this pressure is constant. And due to this pressure, the volume is changing from V1 to V2. Okay. Let's say there is a displacement delta X that has taken place. Okay. And the pressure is what? I'm assuming it to be constant. So we know that work done is equal to force into displacement. Force into displacement, provided the force is acting in the direction of displacement or displacement is taking place in the direction of application of force. But what is force? Force is pressure into area into the displacement that has caused is delta X. So this will be equal to P into A into delta X. But what is A into delta X? It is delta V. So it is P delta V. So work done will be equal to P delta V. Okay. So work done is equal to P delta V. Right. Similarly, if pressure is not constant, okay. If pressure is not constant, but what is happening? What did we say during the expansion of gas? So I'm assuming pressure is not constant, and I'm assuming temperature to be constant. Only then we can plot the graph. If all the three variables are changing at the same time, it will be difficult for us to draw the indicator diagram. So what we are going to do is, we'll take pressure on the y-axis and the volume on the x-axis. So as volume is increasing, pressure will decrease. That's what it says. PV is equal to constant. Right. So P into V is constant means P is inversely proportional to V. So when it is going to decrease like this, right? When it is going to decrease in this way, then from here, if I drop a perpendicular, from here, if I drop a perpendicular, then I will take a small portion among this graph. I'll take a small portion from this graph where here the pressure is constant. So let us say the initial volume of the system is V1 and the final volume of the system is V2. V2 is greater than V1, but T2 is, but P1 is, sorry, V2 is greater than V1, but P2 is less than P1. Right, when this is going to happen, observe what will happen is, if I take this as dV, then the small amount of work done in this process will be equal to P into dV. Right, because that is the area under the graph. Whenever you do integration, you need to multiply the y-axis with the small portion of the x-axis, which implies total work done will be equal to integral of PdV from V1 to V2. So when it is going to be integral of PdV from V1 to V2, can I conclude that work done is equal to area under the PV curve, right? Area under the PV curve and the volume axis. Okay. So whenever you're talking about expansion or compression, it is important for us to draw an arrow mark. So an arrow mark in this direction indicates that volume is increasing and the pressure is decreasing. Right.
Sir,
Tell me.
sir, shouldn't it be the pressure axis? work done. Area,
No, no.
area under the PV curve. and
Area
pressure
under
at-
the PV curve with this axis, no? With this axis. This is the rectangle.
So that is only PV curve, right, on the top.
No, this one. So that PV curve is making an area with which axis? It's a small rectangle actually. It is making with the volume axis only, no? That is the meaning. Okay. Volume axis only. Don't get confused. It is not pressure axis, volume axis. Got it? So this is what happens. So this formula is very important. Remember, okay, this is what you are going to use to solve problems and do some derivations also. Next is a cyclic process. So when I take pressure and volume graph, let's say the thermodynamic process is starting here. First, there is an expansion taking place, and then there is a compression taking place. Okay. Suppose something like this happens from V1 to V2. This is the process of expansion, and this is the process of compression. Right? Now, if I take this as 1 to 2, there will be two works that can be calculated. So work done during expansion. So work done during expansion, if I call it as W1, that will be how much? That is the area under the, that is what? The area under this graph, no? This whole area will give me W1. So area under, I'll take another point, 1, 2, 3, I'll take this one. So area under the 1, 3, 2 curve with respect to volume axis. So what do I mean by 1, 3, 2? 1, 3, 2 means from first position to second position, I'm going through 3. Okay. So have this in your mind. Second, can you tell me what is the work done during compression? Area under the graph 241 with respect to volume axis. Right? Is this clear? So what is happening in the case of W1? There is an expansion. In the case of W2, there is a compression. So here you need to make an important note, which is called as Sine Convention. I have to introduce at this point. Right? You would have learned this in your chemistry. Here it will be slightly different. So when I talk about Sine Convention, there are three important parameters we can calculate about: work, heat, and internal energy. Work, heat, and internal energy. So work done is positive if work is done by the system. Similarly, it is negative if work is done on the system. Work is done on the system. Similarly, when you talk about heat, heat is positive when it is absorbed by the system. Similarly, heat is negative when it is lost to surrounding. So work is done on the system. Sorry, heat is lost to the surroundings. Okay. Similarly, when I talk about internal energy, it is taken to be positive when energy is increased. So when internal energy is increased, then when the internal energy is increased, you take that value to be positive, and when the internal energy is decreased, you take it to be negative. Okay. So having the sign convention in mind, tell me what is going to be the total work done in this process. What is going to be the total work done in the cyclic process? So W1 is expansion. W2, which I will call it as this as W2. So W2 is compression. So when I say work is done by the system, will the system expand or compress? When can something get compressed? When you do the work on the system, or the work is done by the system?
When we do the work.
When you do the work on the system, it will expand or compress. So my question is, when you do the work on the system, will there be a compression taking place or expansion taking place? You think of a small balloon, no? It is compression, right? When it is compression, then you're saying work is done on the system is negative. So in which process, W1 is positive or W2 is positive? You answered it already.
W1 is
W1 is positive. That's it. So the total work done will be W1 minus W2. Means throughout the cyclic process, you need to calculate the positive work and you need to calculate the reverse work. You need to calculate the work done in expansion, you need to calculate the work done in compression and subtract both. That will give you the answer.
Sir, could you show the sign convention for 1 minute?
Yeah. So this is very, very important. If you don't know this, you can't solve problems, you can't do derivations. And one more important point, if you see these sign conventions in chemistry, it will be exactly reverse. So be very careful about this point. In chemistry, because we speak about chemical reaction, there the attributes that are considered are slightly different for sign convention. So be careful.
Sir, in
with
chemistry,
it.
I think they focus on heat, right?
They focus on heat because you concentrate on exothermic and endothermic reactions. Because heat will lead to enthalpy and all those things, right? It speaks about the bond energy. Yes, heat they speak, but you will have derivations with, you will have formulae with respect to work done in isothermal and adiabatic process, right? So during that process of derivation, it will be slightly different. That is what I'm trying to say. Observe it next.
Sir,
What you're saying is right. They mean. Sorry.
Sir, only sign convention for work done will be differ, sir.
I think it is for heat also. Just check it once. I don't remember, but I'm just asking you to be cautious. I'm not commenting on chemistry part, but I know that there is some difference. I don't exactly remember what is the difference. You guys figure it out. I'm clear with what I spoke in physics. This is what is applicable for physics. Okay. Okay. Done. So these are all some important terms. So these are all the basics. Okay. The next question is about what is this first law of thermodynamics? So we saw what is zeroth law. Next, we'll see what is the first law of thermodynamics. So when you take a system like this, right? So it's not a liquid, it's some gas. Now, when you supply heat to the system, right? When you supply heat to the system, what will happen? When you talk about a gas, so when heat is taken by a gas, what does a gas do? Gas expands. Its volume is going to increase because of the thermal properties of matter. So when its volume has to get increased, then this piston has to move up. Accepted. Think of the logic. Heat is being supplied to the system, and when heat is supplied to the system, the gas molecules will the gas will start expanding. When it starts expanding, it has no other option other than pushing the piston to a slightly pushing the piston slightly above its initial position. When this is going to happen, can I say the changes are like this? The amount of heat supplied is equal to the amount of work done by the system plus, when I say the volume is going to increase, it is happening because of the increase in internal energy. Can I say something like this? So the amount of heat that you supply will be equal to the amount of work done by the system plus the increase in internal energy. This is the mathematical statement for the first law of thermodynamics. Okay. It is something like energy conservation. You are giving some energy in the form of heat. That energy is being utilized for two things. What is it? One is for the system to do some work, and the second one is to increase the internal energy of the system. That's it. Right. So this is all about increase in internal energy. So for this class, I'm stopping with this because I've taught so many terms today. So you guys revise all these concepts and come. In the next class, I'll start with some example problems. After that, I'll show you derivation, important derivation for two processes. One is isothermal process, and the second is the work done in the case of an adiabatic process, for which we'll be using the formula integral of PdV. Okay, so revise all these topics and come for the next class. Maximum, I think by next class, this chapter will be over. Then we'll go to 14th chapter, not the 13th chapter. Then we'll go to the 14th chapter, that is oscillations. Then we'll go to 15. At the end, I will explain kinetic theory of gases, because that's a very small chapter and it is not of much importance. But oscillations and waves are very important for your next year. Okay. So that's it from my side for today. Is there any doubt?
No, sir.
Is there any doubt, guys? No. Okay, then we can wind up.
Thank you, sir.